Today we're going to continue working with exponential growth or decay functions. So just as a quick review, when we're looking at a problem, we're going to read it. It's going to always have that real world context behind it. A growth means that it's either going up, it increases, it's growing, it's getting bigger. All of those things are going to recognize that it's going to let you know you're using a growth. A decay, it's going to be, something is losing its value. The value's going down. It depreciates, okay? So those are the things that you're looking for in terms of the real world context to know whether am I growing or am I decaying. Then, just as a reminder, our growth and our decay formulas, they are exactly the same except that the growth has a plus, decay has a minus. And as another reminder, what all these different variables mean. So our A in both represents our initial value or whatever your starting amount is. Our R is the rate, which is always the percent written as a decimal. And our X in the exponent is always whatever your time period is. So far all we've done is take problems and plug in these values. Today we're actually going to start solving them. So let's take a look at some examples. So it says, Daniel's print shop purchased a new printer for $35,000. Each year it depreciates, loses value at a rate of 5%. What will its approximate value be at the end of the 4th year? So, it depreciates or loses value, tells me that it's going to be a decay. So I'm going to be using my y equals a1 minus r to the x. Remember, minus for decay. That tells us it's losing value, it's going down. So my initial value is this 35,000. 1 minus, well, my rate is 5%. As a reminder, if our decimal's over here, I have to move it over 2 units. So my new rate is going to be 0.05. So 1 minus 0.05. And they're looking after the 4th year, so it's going to be the 4th power. So far, this is all we have done. We're now going to take this and type exactly as we see into the calculator. Again, it's just up to that 4th. I'm sorry that it kind of gets a little close. So I'm going to type in my 35000 parentheses 1 minus 0.05 to the 4th power. And I'm going to get 28,507. And we're looking for money, so money is always going to be 2 decimal places. So we have 0.718, well that's going to be 0.72. So therefore we're going to choose choice 3. So again, all we did is what we've always done so far, and I plugged it into the calculator to find my value. Let's take a look at another example. Adrian invested $2,000 into an account at 3.5% interest rate compounded annually. She made no deposits or withdrawal on the account for 4 years. Determine to the nearest dollar the balance after 4 years. So again, we're looking to figure out how much is going to be there. So we're going to plug all of our information in, and then we're going to get an actual number. One thing I want to point out, it says to the nearest dollar. Sorry, I just did not draw a straight line. But to the nearest dollar, that means that we're not going to have any cents on it. So we're going to round it to the nearest whole number. If it had said to the nearest cent, we round it to the nearest cent. Whatever the problem happens to tell you is what you're going to do. So whenever we're dealing with the problem where it's compounding interest, that means the value of it is going up. So it's going to be a growth. So I'm going to start out with my y equals, my initial value is the 2,000. My 1 plus, because it's growth, 3.5. Again, I move my decimal over 2 units, is 0.035. And they asked after 4 years. So again now, I'm going to type this in the calculator. I have 2,000 parentheses 1 plus 0.035 raised to, oops, I have to close my parentheses, raised to the fourth power. We get 2,295.04, so on. But again, it asks to the nearest dollar, so we're going to have to round it to the nearest whole number. So then our answer is going to be this 2,295 with no decimals whatsoever because it says to the nearest dollar. Just one last example. The population of Henderson City was 3,381,000 in 1994, and it is growing at an annual rate of 1.8%. If this growth rate continues, what will be the approximate value of Henderson City in the year 2000? Now, this question's a little bit tricky only because it doesn't tell us exactly how much time. So we have to figure out how much time. So they're telling us from 1994 to the year 2000. So in the past two problems, it just said, oh, in 6 years, in 4 years, in however many years it was in dealing with. Here, we have to figure that out. Well, between the year 2000 and 1994, 6 years passed. So that's the only thing that's going to be different about this problem compared to the last. You have to recognize they're giving you two time values, and we just have to know that that is going to be 6 years. So we're going to plug in, it's growing, the population is growth. They're telling us all this. So we start y equals 3,381,000, 1 plus my 0.18 is 0.018. Again, we said it's 6 years, so it's going to the 6th power. I'm just going to type in exactly as I see. 3,381,000, parentheses, 1 plus 0.0818, close my parentheses, to the 6th power, and it gives us this value. We now just have to carefully look at our answer choices. Of course, we're talking about people, the population of a town, so we can't have decimals when we're talking about people. So our answer, if we round, is going to be, so it's asking for an approximate answers, right? So it's going to be the closest answer that we have here is choice number 2.